Hello, everyone. Welcome to the 2025 PIBBSS Symposium. Our speaker, Matthew Shinkle, will be discussing plateaus in activations.
Awesome. All right. Thank you, everyone who's viewing this currently, as well as anyone who views this in the future. I'm Matthew Shinkle, and I'll be discussing a project I've been working on for the duration of PIBBSS with my mentor, Stefan Heimersheim. I'll be digging into the internals of language models, which is something I'm guessing not everyone who will view this has done before, so I'll try to avoid any really unnecessary technical details. But if you have any questions about anything, feel free to ask them in the chat of this meeting. And then I'll try to get to them, if not during the talk, then in the Q&A period at the end, or you can just ask them at the end. Also, I'm currently recovering from COVID, so if my voice gives out, my apologies. As a quick bit of general background, transformer-based language models, or LLMs, represent information in their activations. So this can be thought of as a set of values in a list or a vector, like these values shown here. And this can be equivalently represented as a point in space, like this here on the right, where each of the axes of the space is one of the activation dimensions in the model, and the position of a point on each of these three dimensions corresponds to the three values on the list. So for example, for an LLM to process a sentence like this one here, the cat sat on the, it first breaks the sentence into a sequence of chunks or tokens, in this case, the cat sat on and the, then converts these tokens into embeddings, which are basically the initial activations, which are then passed into the model. And so these activations pass through the model's layers, gradually transforming the positions of the activations in activation space, and finally predicting which token is most likely to come next, in this case, Matt. So any difference between two tokens or two sequences in the model must be represented as different positions in the model's activation space. So if we want to understand how language models process information, how they understand different contexts, and how they make decisions, the activation space seems like a reasonable place to look. And indeed, a large variety of techniques, including things like linear probes and sparse autoencoders, aim to find linear directions in activation space that correspond to interpretable and behaviorally relevant concepts. And furthermore, attempts to shape model behaviors like steering vectors work by adjusting the positions of activations, again, within the space. You may have noticed the word linear in a lot of those methods, linear probes, linear steering. And indeed, many of these techniques make assumptions about the linearity of representations in activation space. These are not assumptions I'm necessarily trying to disprove, but there is one possible misunderstanding of this, and this is that influencing activations in an earlier layer of a model should lead to linear effects downstream for the model, for example, in model behaviors. And this is something that I would challenge. There are a number of reasons to question this. The first of these comes from areas in philosophy and cognitive science, like concept formation and cognitive semantics. Even continuous features are often related in nonlinear or discontinuous ways to downstream features, categories, or behaviors. For example, a feature for neck length, like here on the right, may vary continuously, but if you're using it to determine whether an animal is, for example, a deer or a giraffe, the relationship from the feature to the category won't be linear. Most deer tend to have fairly short necks, whereas most giraffes have long necks, and so any neck below some threshold is almost certainly a deer. Any above some threshold is almost certainly a giraffe. And only in this narrow overlap in the middle are we really unsure which it is. And this also holds for behaviors. For example, the relationship between outdoor temperature on a given day and what you wear when you leave the house, or if you even leave the house at all. The second reason to question this idea comes from actual experimental results. It's a common finding that continuously steering activations in some direction in an LLM results in nonlinear changes in downstream behaviors, as shown in the results for both of these papers here. So this is the broad question I've pursued in this project. How do language models warp activation space across their computations? Now, this is a very broad question, and there are a lot of facets to it. And as much as I'd love to tackle all of it, for a 3-month fellowship, I decided to focus on a much more constrained problem. Specifically, how do we explain the phenomenon of activation plateaus? So what are activation plateaus? This is a term I believe first coined in this 2024 post by Stefan Heimersheim and Jake Mendel. And the core experiment that they did here is relatively straightforward. So you take two sequences that are identical except for the last token, like these two sequences here, John is going and John is really. You then pass them through the model like normal and record the model outputs. We then take the embeddings for the last tokens in these sequences, so going and really, and interpolate between them, getting either a line or, in the case of spherical interpolation, a curve through the embedding space between these two sequences. We then pass all of these interpolated points through the model with the embeddings of the rest of the tokens for the rest of the sequence the same, and record the model outputs for each of these interpolated points. We then take the outputs for all of these interpolated points and measure how close they are to the outputs for the original sequence A or the sequence B. You can measure how close they are with a number of different metrics like L2 distance or cosine similarity or whatever. But then what we do is we plot these differences for each interpolated point. And so if the relationship between positions in embedding space and positions in model output space are linear, we would expect to see something like this here. And in fact, we do see results like this sometimes. So for example, for the sentences, the house at the end of the street is very, and the house at the end of the street is quite, we see a curve like this here in the middle, which is approximately straight. However, in other cases like this pair here, we see a very different result. Specifically for approximately 40% or so of the interpolation, the model outputs remain very similar to what they were for sequence A. And then in this narrow band in the middle, there's a rapid transition where the outputs go from being very similar to those of sequence A to being very similar to those of sequence B, and then they stay that way for the rest of the interpolation. So these flat regions on either side are termed plateaus because they're areas of low change. And the sharp region in the middle is what we call the plateau boundaries. So what's the purpose of this phenomenon? Why does this occur? A few projects since this original post have suggested that plateaus do appear to have some purpose. They seem to be an intentional thing within the model. So for example, in this paper, they examined how plateau boundaries relate to model size and the duration of model training, finding that both larger models and longer trained models tend to have stronger, sharper plateaus. And this occurs across a variety of different model families. Other work has compared plateaus for real model outputs versus just random activations or activations produced by sparse autoencoders, finding that steering toward real activations, as well as just steering starting from real activations, both produce clearer plateaus than random baselines. So these findings suggest that plateaus appear to have some functional purpose in models, but it's not exactly clear what that purpose is. As I mentioned earlier, this is kind of what I was originally trying to explore with this project, and I actually did a lot of experiments looking at how plateaus relate to things like model features. But the more I dug into this, the more I realized I needed to understand mechanistically where and how the plateau behavior occurs. The hope of this was that such an explanation would enable much more effective experiments for uncovering the functional purpose of activation plateaus, and may itself provide hints at this purpose. To start, I wanted to narrow down where in models plateau behavior emerges from. Transformer-based LLMs are composed of a number of sequential layers, and I wanted to see which of these layers are responsible for the plateaus. So to do this, I took the GPT-2 large model, which is composed of 36 layers, and first replicated the original Plateau experiment. So take two prompts that are identical except for the last token, interpolate between them, patch these interpolated embeddings into the model, and record the model outputs. Except in this case, instead of recording the final model outputs, I recorded the activations in each downstream layer from the interpolation. We could then measure the similarity of the responses in each layer to the responses in that layer at each of the reference prompts and generate a curve like before, but here with a different line for each layer. So in this bottom right plot here, darker lines correspond to recording in earlier layers in the model, and the brighter lines correspond to recording in later layers. So as we can see in the results here, the deeper we measure in the model, the sharper the activation plateaus get, with wider plateaus and narrower, steeper boundaries in the middle between them. So this could mean that deeper layers of the model play a greater role in producing plateaus, or it could be a consequence of the activations passing through more layers. So in a second experiment, I did another variant of this where instead of interpolating in the initial embeddings, I interpolated in the activations of each layer in the model and recorded the model outputs. So kind of the converse of the experiment I did before. And here we see the opposite trend, where the earlier we interpolate in the model, the sharper the plateaus are in the model outputs. So taken together, these two analyses suggest that the main factor that increases plateau sharpness is the number of layers between where we interpolate and where we record. And we can actually test this specific hypothesis more directly by combining both of these methods. So we interpolate in some layer in the model and record a specific number of layers later in the model. And we find the plateau sharpness is strongly influenced by the number of layers between the interpolation and the recording, rather than emerging specifically from a specific layer or set of layers in the model. We do see some evidence of sharper plateaus from the earlier layers, which is shown by the darker lines in these three plots. But I think the primary factor here seems to be the number of layers that the activations pass through. So we found that the plateaus emerge gradually across model layers. But comparing different layers is just one way to break down a model. Another way is to look inside of the layers. So if you're not very familiar with transformer models, each layer can be broken down into two different blocks. These are called the attention block, which moves information primarily between tokens, and the MLP block, which transforms representations within individual tokens. So given these differences in roles between these two components, it's possible that plateaus emerged primarily from one or from the other. To investigate this, I did an experiment where I froze the outputs of all of either the attention blocks or the MLP blocks and performed the main plateau experiment again. This word freezing is often used in the context of model training, where it means freezing the model weights, meaning that they're not allowed to change during training. Here we're not training the model, we're using a pre-trained model, and the weights aren't changing. So what I'm actually freezing here is the output activations. Specifically, I'm recording the outputs of the attention or MLP blocks for sequence A, and then freezing them to only ever output those activations, regardless of the interpolated inputs. And because the final outputs of a transformer model are a combination of the outputs of the attention blocks and the outputs of the MLP blocks, freezing one of the outputs of one of these means that any variation in the final model outputs must be a consequence of the non-frozen component. So for example, here I froze the attention blocks, as you can see by these ice graphics I put over here and spent too much time on. And when I plot the resulting model outputs, we see that the activation plateaus are basically unchanged. But in contrast, if we instead freeze the outputs of the MLP blocks while allowing the attention outputs to vary, the plateaus almost entirely disappear. So taken together, these are pretty strong causal evidence that changes in the outputs of the MLP blocks are the primary source of the activation plateaus that we observe. So we've narrowed down this phenomenon to the MLP block specifically, but we can go even deeper. MLP blocks are generally composed of two main parts: an initial layer norm operation, which basically rescales the input data, and a set of two fully connected layers with a nonlinearity like ReLU in the middle. So do plateaus emerge from the layer norm operation, these fully connected layers, or both? I looked at this a few different ways, but I think the one that shows the results most clearly and most simply is by examining activation plateaus in a copy of GPT-2 that is functionally similar to the original one, as similar as possible, but with the layer norm operation completely removed from the model. There's a whole suite of these GPT-2 models available in connection to this paper shown here on the right, which I found very useful for this part of the project. And if we perform the same experiments I've described thus far, but on the version of GPT-2 with layer norm removed, we find very similar plateau curves, despite the fact that we've now completely removed this layer norm operation. So this suggests that it's actually the fully connected layers of the MLP blocks that are responsible for producing plateaus. So we've now narrowed down the source of plateaus from the full model to the fully connected components of the MLPs of each layer. But what is it specifically about the MLPs that explains the plateaus? In other words, what is different about the MLP outputs for points lying within a plateau versus on one of the boundaries between plateaus? There are a number of differences here, but I think there's really one thing that explains how plateaus are produced by the MLPs. So think about it this way. Within the plateaus here and here, all inputs are being mapped to very similar output locations despite varying in input space. In contrast, within this boundary region here, even inputs that are relatively close to each other in input space end up mapped to fairly different locations in the output space. We can actually measure this by looking at the magnitude or step size of the change in activations as a function of each input step. And we find this huge jump here in the middle, which grows larger and larger as you're looking in deeper and deeper layers of the model. So another way to put this is that plateaus correspond to areas in the MLP input space that are very insensitive to small changes in the inputs, and boundaries correspond to areas in the input space that are very sensitive to small changes in the inputs. A good way to measure this sensitivity is to compute the Jacobians of the transformations that the MLPs perform. For anybody not familiar, Jacobian is a matrix measuring essentially the sensitivity of each output to changes in each input. Jacobians are often computed for model weights during training, but here we're computing them for model activations. Once we've computed the Jacobians at each step, we can aggregate over them by just taking some aggregate measure, in this case the L2 norm, resulting in a single number per step, describing the overall sensitivity of outputs to small changes in the inputs at that point. We can then plot these values, and we find that Jacobians have very low magnitude for steps lying within the plateaus, and this large bump in magnitude right at the boundaries between plateaus. So this is a pretty clear effect, particularly in earlier layers, which are the darker lines here. And this really validates the hypothesis that plateaus and boundaries emerge from low and high sensitivity regions in the input space of the MLPs. I also think it's important that this is not just a measurement of the activations themselves, but it's actually a causal property of the MLPs themselves that's explaining this sensitivity. This is just an illustration, but I think this is potentially helpful for tying all this together. So for the MLP of each layer, you have points moving along a path in the MLP input space, with the Jacobian norm or sensitivity being highest in the middle. As you move through the layers of the model, this effect actually accumulates multiplicatively, with points in low sensitivity areas remaining close together and points in high sensitivity areas being pulled farther apart. If you move along the interpolation path of model inputs, this results in slow or low magnitude changes for most of the interpolation, with rapid changes here in the middle. And this effect is amplified across layers. And if you plot this as a function of distance from prompt A versus prompt B, you get a result that's highly similar to the plateau plots that we actually observe. One of the things that I find exciting about this explanation is that it links the phenomenon of activation plateaus to a number of other extant research areas. One of these areas is efforts to characterize general neural network models and their behaviors as a function of ReLU splines. So this line of work leverages the insight that neural networks with piecewise linear activation functions, like the ReLU activation function, can be characterized based on the decision boundaries of each individual neuron. Or in other words, the locations in input space where neuron activations cross the threshold of their nonlinearity and change from either 0 to greater than 0 or from greater to 0 back to 0. This essentially defines a spline or hyperplane in the input space for each neuron. Papers from this research area have shown a number of very interesting relationships with model decision boundaries or splines and model behaviors like grokking, including observations that well-trained models tend to bunch up these splines in areas that separate model classes. I wanted to see if we can extend this kind of analysis to the MLPs of large language models. Specifically, I was curious whether there was a relationship between spline density and the orientation of splines and our observed activation plateaus. If so, based on the previous results from image classification models that I just mentioned, this would suggest a relationship between plateau boundaries and semantic distinctions within LLMs. To explore this, I took the activations at each interpolation step and computed which splines lay within a pre-specified radius around these activations, like here on the top right. And indeed, when I look at the number of splines within this radius at each step, we see a big jump at the same places where the plateau boundaries lie. In addition, if we look at the orientations of the splines within this radius, we see a substantial increase in the relative alignment of these splines, both with each other and pointing orthogonally to the step direction. So this is basically kind of like a wall of these hyperplanes that you're passing through as you're hitting the plateau boundaries. And so note that these are both what we would expect from the studies I just mentioned, specifically if plateau boundaries correspond to some sort of decision boundary or semantic distinction in LLMs like they do in classification models. Just as another example of these results connecting to other research areas, here's a work from 2023 showing that classification models learn to magnify space around decision boundaries as measured via properties of the activation Jacobian, pretty similar to the Jacobian analysis that I just did. So I think I've generally achieved my goal of finding a mechanistic explanation for how activation plateaus actually emerge. And furthermore, these findings connect the plateau phenomenon to other areas of research and open up potential avenues of exploration. But what is the actual purpose of plateaus? Specifically, could we predict when they will or won't occur? How can we characterize their exact relationship to model features? And I actually did a lot of different experiments related to these questions. But kind of unfortunately, I did basically all of these within the first 2 or so months of the fellowship before I developed this mechanistic understanding. So if I could do it again, I would probably have done a lot of these somewhat differently. I'll go over these experiments briefly in case it sparks any ideas for anyone else thinking of doing experiments related to this down the line. But unfortunately, most of these are fairly null results, in their current form at least. In one of these experiments, I wanted to see if plateaus emerge more clearly along dimensions in activation space that correspond to continuous versus categorical features. To do this, I used a dataset of world locations from this paper by Wes Gurney and Max Tegmark. This is a very cool paper which showed that you can use linear probes to find directions in the activation space of LLMs, which closely correspond to latitude and longitude of real-world locations. Another way to think about this is that there is a plane that you can find in the activation space of LLMs, which, when points are projected onto it, the points are arranged like a 2D map of the world, which is cool. So these latitude and longitude directions are examples of continuous feature dimensions. In order to find a categorical dimension for the same features, I used an additional set of features for each location that indicate their structure type. So for example, bridge or restaurant. And so critically, this should be relatively independent or not correlated with the latitude and longitude locations. I then ran a linear discriminant analysis to find a direction and activation space that best separates these locations into clusters based on these structure types. And this part worked pretty well, consistently finding single directions and activation space that enable training of linear classifiers with at or greater than 90% accuracy um, of classifying these locations based on their structure. I then took a random one of these locations and gradually steered activations in response to that location along either one of the continuous directions, so latitude or longitude, or along one of the along the categorical direction based on structure type. And what I was hoping to find was some kind of difference in the resulting activation plateaus from steering along these different directions. Unfortunately, what I actually found was that neither of these consistently elicited activation plateaus. I'm still not exactly sure why this didn't work. It's possible that points are for all these locations are just too close together in activation space. I found that even interpolating between two locations located the farthest apart in activation space still yielded fairly weak plateaus. And if we really found that all of these locations are positioned within a single plateau, that would actually be really interesting. It's also possible that there was an effect, I just didn't use sensitive enough methods to measure it. After all, these linear representations of latitude and longitude only emerge some ways into the model. So it's possible that steering activations in that layer just didn't pass the activations through enough layers to produce strong plateaus, or there may be some other explanation. So I think this is still a promising direction, just with some additional explorations needed. I also tried to see if I could uncover any patterns of when activation plateaus do or don't occur just by testing a huge number of pairs of tokens or of prompts. The issue I ran into here was since we're passing both the tokens and all of the interpolated points between them through the full model for each pair of sequences, this can quickly become very computationally expensive. And I think this is an area actually where Jacobian-based analyses based on the mechanistic explanation are particularly promising. So concretely, if you think about the Jacobian for the MLP component, the Jacobian is a function of two things. So you have the weights for the two linear layers, which here I'm calling W1 and W2, as well as the spline code. So this is a list basically of the neurons that reach their threshold for their activation function and output some value greater than 0. This is because only neurons that are on for a given input influence the Jacobian at that point. So if all you care about is something like the sum or L1 or L2 norm of the Jacobian, you can actually pre-compute the product of these weights matrices and use them for different spline codes. So you can compute an aggregate metric like the sum of the Jacobian by summing just the values from this product at the active neurons. And this can increase the efficiency of the Jacobian computation by something around 12,000 times. And so this allows all sorts of cool analyses. For example, you could take all of the splines, use them to compute different intersections, faces, polytopes in the input space of the MLP, and then explore questions like which neurons would I have to turn on or off in order to push a given activation onto a plateau, so an area of low Jacobian, or can I find a path of low or of high slope from point A to point B just by turning some of these neurons on or off and measuring the changes that they produce in the Jacobian. So I think the fact that plateaus can be tied to the MLP Jacobians opens up a lot of analyses of the sort that would be previously infeasible. And finally, I did some explorations of whether steering along feature directions from sparse autoencoders produce stronger or more frequent plateaus than does steering along other directions, for example, in random directions. This yielded some interesting results. For example, I found that steering activations along the directions of SAE features that are frequently active in a big set of inputs tends to produce much larger changes in activations than does steering along more infrequently active SAE features. And in another analysis, I found that steering along SAE features that are active for a given input tends to produce measurably different plateaus than steering along inactive feature directions. And this suggests that plateaus could potentially be used as a means of uncovering meaningful feature directions, which I think would be pretty exciting. So to tie everything together, through a series of experiments, I found a mechanistic explanation of how the phenomenon of activation plateaus occurs in large language models. Specifically, I found that plateaus emerge from the MLP blocks in each layer and can be explained by regions of low magnitude Jacobians producing plateaus and high magnitude Jacobians at the boundaries separating them. I find that this effect accumulates over model layers, resulting in sharp plateaus and boundaries in the model outputs. This not only explains how plateaus occur, but connects them to other areas of active research um, with connections to these areas suggesting a relationship between plateaus and learned boundaries of classification models. My attempts to relate plateaus to model features has thus far yielded somewhat mixed results, but these findings suggest interesting techniques and directions for future experiments. If you find this kind of stuff interesting, feel free to reach out. I personally find all this stuff really interesting, and I've quite enjoyed working on it. And my mentor for this project, Stefan, frequently mentors people as a part of a couple different programs. But if you're interested, I would especially recommend considering applying to PIBBSS. Taking part in the PIBBSS Fellowship has been immensely valuable to me, both for building knowledge and experience and for creating the connections I've needed to transition into AI safety and interpretability research full time. And I think that I'd be significantly worse off had I not participated. So thank you to everyone at PIBBSS, my mentor, Stefan, and everybody I've chatted with during my time in the program. And thank you to everyone listening to this talk. Thanks.
I've got a question.
Awesome.
So in the example right at the beginning from Stefan and Jake, they find that there's a boundary between the token really and the token going to.
Yes. Yeah.
Yeah, which is like, yeah, you should expect like the model to behave very differently depending on which of those words there is, because they're like kind of grammatically different.
Yes. Yeah.
Do you know if there were just like two concepts that differ merely semantically that also exhibit sharp boundaries?
Yeah. So some of the experiments that I didn't talk about in here, I've done a lot of stuff looking at, for example, can plateaus be predicted by like the semantic similarity between tokens, whether they're basically synonyms or not, or you can take words that are synonyms in one shared context, but in a different shared context, they're no longer synonyms. I did a bunch of analyses of this sort, and like they all show some degree of an effect. So it seems like tokens that are semantically similar and which have like similar model outputs tend to be less likely to produce plateaus. But this is not This is not something that's just like if you plot it, it's just like a straight line. It's a pretty messy signal, and so that suggests to me that there's something significantly more going on here in terms of whether plateaus emerge or not. Does that answer your question?
Um, yeah, but also I was looking to see if you have any like examples. Um,
Um, I don't believe in these slides. I looked at some other stuff like, for example, if you take a trio of tokens or of sequences where two of them are substantially differ but vary along some continuous dimension. So like the weather outside is hot or the weather outside is cold, and then you take a third token that is just about as dissimilar as those, but does not vary along some continuous dimension. So like hot or like red, which is like kind of similar to hot, but not along like a continuous axis and fairly different than cold. And looking at do we see plateaus in one of these, not the other? And so you do find that, for example, between hot and red and cold and red, you see clearer plateaus than between hot and cold. So this does suggest that plateaus correspond to more like categorical distinctions. But I think this requires more systematic um, testing over like a big set of prompts in order to see if this uh, partially explains where plateaus occur or not.
okay, thanks.